Welcome once again. So in this video, I'm going to be starting on the first chapter. The first chapter is about numerical differentiation. Okay. Of course, the year is now 2020, right? I will be correcting that. All right. Now, in chapter 1, we start off with this motivation, right? So suppose you have the following data about a chemical reaction. So this could be maybe a chemical engineer collects this data. There is some time and a measurement of the volume produced by a chemical reaction, right? So the timing is, the recording is at 15 minutes intervals. All right, and these are the volume that you get from a certain reaction. All right, so this is normally what happens in practice. You have data, okay, and you want to say something about how the reaction is going on, for example, right? That could be to calculate the rate at which the volume is growing. All right. So in terms of mathematics, that would be dv dt, which is the derivative of v with respect to t. Okay. The reason why you would want to find the rate at which v is growing is maybe you want to create the space, okay, to collect this whatever is being produced in this region. All right. So if this example doesn't make sense, all right, at least the mathematics will make sense, all right? So this is like a fictitious example, right? So we are trying to find dv dt. How do we do that? We only have digits, numbers, right? This is where numerical differentiation comes in, all right? So this, as you can see here, there is no formula for v, and so we can't do it analytically. So we have to do it numerically, and which is the point of this lecture, right? Now, that is how derivatives arise in practice, right? But let's look at the definition of it, right, which you probably have seen before. Now, the derivative of y with respect to x is written as f prime, and it is found by doing this limit. All right, so you take this limit when h is small, when h goes to 0, or when h becomes smaller and smaller, right, then you get this derivative, right? Now the next thing that you need to know is all right, suppose we wanted to find these two values, then we could find these from the Taylor series expansion. The Taylor series expansion gives you f at x plus h in terms of f at x and its derivatives. If you don't know what the Taylor series expansion is, then you probably want to open a book in calculus, or maybe Google it somewhere, right? If you have forgotten the Taylor series expansion. In these notes, we assume that you know it. Okay, and you need to know it because it is central to everything that will happen in this chapter. Everything is about this formula, okay? And you will see why as we go from chapter to chapter, right? Now, if we want to find this, then we can rearrange this formula and write it like this, right? And if we discard this term, or in other words, if we chop this term, if we throw away this term, then we only end up with this first part. Okay, so since we have removed this term, it is now an approximation, right? So this term will approximate this, okay, which is what we have in 3. This formula for approximating the first derivative is called the forward difference formula. Forward difference formula, all right? And some things that you can see from this is that it is a first order approximation. the order is found from this. Okay, you look at the h here. So since we only have h, only one h here, that makes it a first order approximation. And its error again you find from the first term that you throw away. Okay, this is the associated error. Okay, I will explain to you what that epsilon means. Now you can also write the Taylor series expansion as this, right? So instead of plus here, we now have minus, right? So we had plus here, now we have minus, right? And it can be written like this, right? You can replace plus h with minus h here. So if you replace plus h here with minus h, everywhere you see h, you replace by minus h, then you will get this. Okay, now again, if you rearrange and find this term in terms of all the other terms, then you get this. Okay, again, if you discard this term or chop away this term or discard this term, okay, then you remain with this term. So because you have chopped this, it is no longer equal, but it is now an approximation. Okay, and this approximation is different from what we have seen before. This one is called the backward difference formula, okay, for approximating with prime. Why is it backward difference? It's because of these two terms, x and x minus h. Okay, so as you can see that this term x minus h is before x, right? So that means it's backward difference formula. It is for that reason that it is backward. This one is forward because this term here, x plus h, is more than x, or is ahead of x. So that makes it a forward difference formula. Right? You need to be able to distinguish between the two of them. Right? Now you can also see that here we have a first order approximation, because from here you see that we only have h here in the first term that we discard. So that makes it a first order approximation. The associated error is also this, but with x written in terms of epsilon. Right? This is similar. Now you can do other things. Now if you add the two formulas 2 and 4, so if you add these Taylor series expansion 2, if you add it to 4, which is now with minus h here, you add the 2, you rearrange. You can also write, you can also find the first derivative. Okay, you can write it like this. Again, if you discard this term, you're only going to be left with this, and so it's an approximation. Okay, it's another approximation. But notice that here we now have h squared, so that makes it a second order accurate method. Okay, so this method is second order because of these 2. The 2 there makes it second order. And also this approximation is a 3-point formula. Okay, it's a 3-point formula because in order to find this, you need the f at x plus h, f at x minus h, and also fx. Okay, though it's not given here, it's implicit, but that makes it 3-point because you need 3 terms, 1, 2, and f at x. Okay, it means the forward and backward methods are 2-point formulas. All right. Now you can also approximate the second derivative. How would you do that? Now in this case you are going to add 2 and 4. Remember here we subtracted, we got the first derivative, if you add 2 here and 4, you are going to get an approximation for the second derivative. Okay, you are going to get it like this. Okay, once you have an approximation, once you have this, then you can immediately write down the order and the associated error, right? This is second order because, again, as you can see here, you have h squared, so that 2 there makes it second order. And also the error is again this, but being evaluated at epsilon. Okay, here at epsilon. So the epsilon, unfortunately it is not written in anywhere in these slides, but the epsilon here, you can find it as follows. So epsilon is any number between x plus h and x minus h. Okay. Similarly, for an approximation like this, the epsilon is a number between x and x minus h. The notes will are clearly written so that you can see that. All right. Now, let's look at an example. Suppose we have f like this, and we want to find the first derivative at 1, right? We are going to approximate this. So remember, if it is analytically, we would have to do a limit as h approaches 0, right? So if you are doing an approximation, it means you pick h's that are small, okay? Small. As you can see, these numbers are small, and they are progressively becoming smaller, right? So that is what we mean by approaching 0, right? They are getting smaller and smaller, okay? So they are on their way to becoming 0, right? So you pick a small h and then you put it in this formula. The central difference formula is this one. So remember, we are finding f prime. This is the central difference formula. Okay, so we're going to use this formula, which is 6. It is what you have here. We pick an h like this. This is small, and then we are finding it at x equal to 1. Okay, so our x is 1, h is this. We substitute. Okay, we substitute and simplify. Remember, the f is this. Okay, you do that, you simplify, you get that. You repeat this for different h's now. You make it smaller, you make it even smaller, you make it even smaller. All right, so you are going to be changing this part, and this part, and then simplifying. Right? To see that you are in the right direction, you would have to compare it with the true solution. The true solution is what I referred earlier as the analytical solution, right? So basically, you differentiate this like you would do as if you were in high school, all right? You differentiate this, you get this. Once you do that, you substitute at 1, because that is what we want from here. Substitute at 1, again simplify this in your calculator, you get this. Now if you compare with this and that, you see that your approximation is not that bad, right? Why is that so? That is because it is correct to 1 decimal place, right? You see, you have the 2, you have the 2, here you have the 2, now you have 3, and then, you know, everything else is different. So it's correct to 1 decimal place. It's not bad, right? If you don't like 1 decimal place accuracy, then you probably get something better if you use h equal to this. Okay, you get something even closer to that. All right, so that is all I wanted to say for now. In the next video, I'll be continuing from there.